All right, if you're doing A-level physics, you know electric circuits can be a real headache. But honestly, they don't have to be. In this explainer, we're going to break down all the core concepts one by one to make sure everything clicks so you're totally ready for your exams.
So, here's the game plan. We're starting with the absolute fundamentals: voltage, current, and resistance. Then, we'll get into the two laws that rule every circuit, see how that works for series and parallel resistors, check out how real-world components actually behave, and then wrap it all up with how real batteries and circuits work. Let's jump right in.
Okay, let's start with the absolute bedrock of electronics. You've got to get your head around these three concepts: current, potential difference, and resistance. Seriously, they're the alphabet we use to spell out everything that happens in a circuit. First up, current, which we call I. Think of it like water flowing in a pipe. Current is just how much water, or in our case, charge, flows past a single point every second. The formula, I equals delta Q over delta T, is just the math version of that. How much charge, Q, passes in a certain amount of time, T. Simple as that.
Next, we've got potential difference, or what everyone just calls voltage. So if current is the flow of water, voltage is the pressure pushing it. More pressure, more flow. The official definition is the energy transferred per unit of charge. So a 9-volt battery? That means it's giving a 9-joule kick of energy to every single coulomb of charge that makes the trip.
And rounding out our trio is resistance, or R. To finish our water pipe analogy, resistance is like a narrow section or a bit of gunk in the pipe. It's just a measure of how much something fights against the flow of current. The higher the resistance, the tougher it is for that charge to get through. And we calculate it simply by taking the voltage across something and dividing by the current going through it.
Now, these three are all connected by the famous Ohm's law, but here is the critical part that trips so many people up. Look at the end of that sentence, given that physical conditions are kept constant. That simple V equals IR relationship, it only works for some materials, and only if things like temperature stay the same. You have to remember that because it's going to be super important in a few minutes. Okay, so V, I, and R. That's our vocabulary. Now it's time to learn the grammar, the two unbreakable laws that control every single circuit out there. I don't care how complicated it is. If you can get these two laws down, you can figure out any circuit diagram they throw at you in an exam.
And what's really cool is that these circuit laws aren't just random rules somebody made up. They come directly from two of the most fundamental ideas in all of physics. You can't create or destroy charge, and you can't create or destroy energy. In a circuit, all you can do is move them around or change their form.
So, that conservation of charge rule gives us Kirchhoff's first law. People also call it the junction rule, and it's super intuitive. All it says is that whatever amount of current flows into a point where wires meet, well, the same total amount has to flow back out. This means in a simple series circuit with no branches, the current is the same all the way around. But in a parallel circuit, the current has to split up to go down the different paths.
And the conservation of energy rule gives us Kirchhoff's second law, the loop rule. Here's a good way to think about it. For any complete lap around the circuit, all the energy the battery gives to the charges has to be used up by the components. So all the voltage drops across the components have to add up to the voltage gain from the battery. In a series circuit, that means the voltage gets shared out. But in a parallel one, each branch makes its own private loop with the battery, so every branch gets the full battery voltage.
Right, let's put those two laws into practice. Using nothing but Kirchhoff's rules, we can actually figure out the exact formulas for adding up resistors when they're in series and when they're in parallel.
For resistors in series, this is the easy one you'll be glad to hear. We start with Kirchhoff's second law. The total voltage is just all the individual voltages added together. That's step one. Then we use his first law. There are no junctions, so the current I is the same everywhere. That's step two. Now we just swap in Ohm's law, V equals IR, into our voltage equation. See how I is in every single term, we can just cancel it out, which leaves us with the super simple result. The total resistance is just R1 plus R2 plus R3 and so on. See, it's a perfect demo of how the laws work together.
Okay, for parallel, we just flip our thinking. We start with Kirchhoff's first law. The total current splits, so it's the sum of the currents in each branch, step one. Then we use the second law. The voltage V across each of those parallel branches is the same, step two. Now we sub in Ohm's law again, but this time arranged as I equals V over R. And since V is the same for every term, we can cancel it out and we're left with that famous reciprocal formula. Here's a killer exam tip. The total resistance in parallel is always smaller than your smallest individual resistor. It's a great little sanity check for your calculations.
Up to now, we've pretty much been pretending that resistance is just a fixed number. But in the real world, a lot of components are what we call non-ohmic, which just means their resistance changes. And the best way to see this is to look at their current voltage graphs, or their IV graphs.
First, let's look at that ideal case we were talking about earlier, an ohmic conductor, like a normal resistor, as long as it stays at the same temperature. Its IV graph is a dead straight line going right through the middle. The slope is constant, which tells you the resistance is constant. It follows Ohm's law perfectly.
Now for something that absolutely does not obey Ohm's law, a diode. The best way to think of a diode is as an electrical one-way street. In the forward direction, you give it a tiny little push of voltage, the threshold voltage, and boom, the gate opens and current flows easily. But if you try to send current the other way, the reverse direction, the gate slams shut, the resistance shoots up, and basically nothing gets through.
So what about something like an old-school filament light bulb? Well, as you push more current through it, that tiny wire inside gets really, really hot. When that happens, the metal atoms in the filament start vibrating like crazy, and it just gets harder for electrons to fight their way through. So, as the bulb gets hotter and brighter, its resistance actually goes up. And that's why the graph curves over like that.
A thermistor does the exact opposite. Specifically, we're talking about an NTC, or negative temperature coefficient thermistor. The name literally tells you what it does. As the temperature goes up, its resistance goes down. It's made of a special semiconductor, and as it gets hotter, it actually releases way more charge carriers. That makes it easier for current to flow, so its resistance drops.
All right, for our last section, let's bring this all into the real world. We're going to apply everything we've learned to practical circuits and finally look at what is really going on inside a battery.
You know, we talk about the voltage of a battery, but the proper physics term for the total energy it can possibly provide is electromotive force, or EMF. Think of it like the sticker price on a car. It's the absolute maximum, ideal energy the battery can give to each coulomb of charge before any gets lost along the way.
So why does any energy get lost? Well, because every real battery is made of stuff, chemicals, metals, and that stuff has its own resistance. We call it internal resistance, and we use a little r for it. As current flows through the battery itself, electrons bump into atoms inside, wasting energy as heat. This creates a voltage drop inside the battery, which we call lost volts.
And this leads us to the big takeaway. The total EMF that the battery supplies gets split into two parts. Some of it is the useful voltage that actually gets delivered to your circuit. We call that the terminal potential difference, or V. The other part is wasted inside the battery as those lost volts, V. So the total EMF is just the useful voltage plus the lost voltage. This idea leads us to a really clever and useful circuit, the potential divider. If you put a couple of resistors in series, we know that total voltage gets shared between them. By choosing the right resistors, we can build a circuit that taps off a very specific fraction of the supply voltage. This is super useful for things like light sensing circuits or temperature controls. Okay, to wrap this all up, I want to leave you with a challenge to see if you've really got it. Think about a car. You turn the key to start the engine, and for just a second, the headlights dim. Using what you now know about EMF, terminal potential difference, and internal resistance, can you explain exactly why that happens? If you can nail that, you'll know you've got this topic down.